All right, welcome to Lab 10 for the SSRI. SSRI stands for Single Spherical Refracting Interface. So basically we're looking at one surface that borders two different indices of refraction. And this is typically a curved surface, which causes refraction. We know that a plane surface would just obey Snell's law. A curved surface can actually have optical power that can cause rays to focus or defocus, converge or diverge, like we'll see in lab. So we need to describe the index of refraction on each side. We'll label those N1 and N2, assuming that light is traveling from left to right. Now we don't actually have any single spherical refracting interfaces for lab, so we're going to substitute them with a plano-convex lens that looks like this. It has a planar surface and then a convex surface. This is typically labeled PCX, or plano-convex, because it has one planar surface and one convex surface. So again, that'll be our effective SSRI for lab. We want to think about why that works as an SSRI. Again, with light traveling from left to right, we can see that rays coming in, when they hit this planar surface, Snell's law says they're going to go straight through. So there's no refraction happening at that first surface, as long as we have parallel light in. So parallel rays coming in are not going to bend at that first surface because they're all at normal incidence. However, this lens will have some positive power causing these rays to converge, and that's going to come from the fact that when they hit these curved surfaces, there will be some refraction. So there is refraction at the second surface, the curved surface. There's no refraction happening at the planar surface. Almost wrote refraction. If we look at our diagram showing these powers, or the index of refraction N1 and N2, got those labeled up here, there's an equation for the power of the SSRI, and that's given by P equals N1 minus N2 over R. Now in this case, N1 is the first index of refraction, N2 is the second index of refraction. Again, we've drawn this as light going from left to right. R is going to be the radius of curvature. And that radius of curvature has a sign convention that matches our previous sign conventions. If it's negative, that means it's upstream. If it's positive, that means it's downstream. So radius of curvature. I've drawn these here as negative. So we can say like negative R would look like this kind of a shape. Positive R would be this kind of shape, because the center of curvature would be left for the negative case. This is R, and the center of curvature is to the right here. Again, both of these would be assuming light is traveling this direction to the right. Now we're going to skip a portion of part 1 for the lab. You should still measure the power using the location of an image formed by these lenses, but we won't do the lens clock measurement in lab, but I'll talk through that here just so you have that information. A lens clock is an instrument that will measure the radius of curvature by pressing down on the surface in 3 different locations, and using the different measurements of these distances, the lens clock will read out the power. So it has a little dial that will point to a power reading, and that dial will swing around in different directions, depending on how far in this middle point is pressed because of the curvature of the surface. Now that lens clock has to be calibrated, so the lens clock assumes a certain power, or a certain index of refraction for the lens, which is 1.53. some lenses might have an index of 1.53 and some might not. So we have to calibrate the power and the radius differently. You can measure the power from the location of an image. So you'll do that in the lab anyway for each SSRI using image location. And then we're going to convert to radius using lens clock. So normally you would do all of those steps in lab. We'll skip some of those this week just to save a little bit of time, and we'll give you those measurements. We could do this conversion based on solving that earlier formula. The lens clock assumes an index of 1.53, so our index 1 is air, our index 2 is 1.53, and the power reading on the lens clock would be given by PLC. So this is the lens clock reading. And we can then just calculate and solve for R. So if we simplify this equation a little bit, this is just negative 0.53 over the lens clock reading PLC, and that would give us the radius of curvature for our SSRI. You'll have two lenses at your desk. One of them is approximately 4 diopter, one is approximately 11 diopters. And for the 4 diopter lens, the radius is 13.25 centimeters. And that corresponds to a lens clock reading of 4 diopters, which actually tells us that the lens clock is assuming the correct index of refraction for that lens. However, the 11 diopter SSRI does not have that same index of refraction, so its radius is actually 5.3 centimeters, because the lens clock reads 10 diopters, and the lens actually has an index of refraction of 1.58. So again, the lens clock reading is not the actual power. It's basically a converted power assuming a certain index. And so for the 4 diopter lens, that index is correct, and the power on the lens clock matches the actual power of the SSRI. For the 11 diopter, that the actual power is different from the lens clock reading power, which indicates the index of refraction is different. So these indices of refraction you could calculate by carrying out this calculation twice. But like I said, we'll skip that step from the end of part 1, so you can shave a little bit of time off of the lab this week. For the rest of the lab, we'll look at combining these SSRIs into a combination, as well as looking at how they change their power when they're placed in water.